Alright, in today's lesson, we're going to take a look at graphing rational functions which have quadratic asymptotes. So previously, we had looked at rational functions which have slant asymptotes, and if you missed that lesson, I'll link that in the top right-hand corner. But what we're going to be looking at now are rational functions which have what's called a quadratic asymptote. These functions are such that the degree of the top is exactly 2 more than the degree of the bottom. When that happens, we have what's called a quadratic asymptote. So again, just to remind you, slant asymptotes exist when the degree of the top is exactly 1 more. Now we're looking at the situation of having exactly 2 more. What does a quadratic asymptote look like, and what do those graphs look like, the rational function graphs, when they have these quadratic asymptotes? So let's go ahead and take a look at graphing the following rational function. Take a look at this rational function here. You still want to approach this question just like the others. You want to look to see whether there's any factoring that can be done right away. So looking at this question, I see right away I have difference of cubes. So this will factor into x minus 1 times x squared plus x plus 1. And we take that entire expression and divide it by x. Now that this is factored, we can go ahead and find our x-intercepts. My x-intercept happens when the top is 0. That happens when x is 1. You'll notice the discriminant for this quadratic. If you go ahead and calculate your discriminant, you'll find that it's negative. So this has no real roots, so the only x-intercept is 1. Looking at my y-intercept, we're going to go ahead and evaluate the function at 0. And you'll see here that the function is actually undefined at 0, right? We're going to be dividing by 0. So this does not have a y-intercept, but because of it is undefined, that means we have a vertical asymptote at x equals to 0. Again, the degree of the numerator is larger than the degree of the denominator, so this has no horizontal asymptote. Similarly, it does not have a slant asymptote, and we're going to go ahead and discover what the quadratic asymptote is here. So again, the process is discovered through long division. So going ahead and going through long division here, you see it's quite quick. It ends up breaking up here. Our quotient is x squared, and our remainder is negative 1. Now, by the division algorithm, we have the following. And you'll see here, by the division algorithm, we have our polynomial x cubed minus 1 breaks up into the divisor times its quotient plus your remainder. Now, we're not interested in x cubed minus 1. We're actually interested in our function r at x here. So I'm going to go ahead and divide across by x, giving us. And you'll see here, when we divide across by x, we've created now our rational function r at x. These values here will cancel off. The x's will cancel here. And we're left with the following. So I end up getting here r at x is going to equal x squared minus 1 over x. Much like your horizontal asymptote, which exists as x gets infinitely large or infinitely small, we will also let x get infinitely large or infinitely small to find our quadratic asymptote. So as x gets infinitely large or infinitely small, we can see here that the expression 1 over x will tend towards 0. 1 divided by a really large number or 1 divided by a really, really small number will tend towards 0, which means that our function, our rational function r at x, as x goes to plus or minus infinity, will tend towards x squared. So therefore, this rational function has a quadratic asymptote at x squared. Let's put this all together and graph. So going ahead here, I've listed all our information: x-intercepts, y-intercept, the vertical asymptote, no horizontal, and we do have our quadratic asymptote. I'm going to go ahead now and graph our vertical asymptote and our quadratic asymptote. Doing so, we get. So going ahead here, I've graphed my vertical asymptote and my quadratic asymptote, y equals x squared. I also have an x-intercept at 1. That's going to be somewhere around here. And now we have to graph our rational function. So the same techniques apply. What you want to do is focus your attention on your vertical asymptote, and we want to ask ourselves, am I coming from below or is it coming from above? As I approach here my x-intercept of 1. We could pick a number between 0 and 1, right? This is my vertical asymptote here is 0. This is 1. Pick like a half. Evaluate the function r at a half and see whether we get positive or negative. Doing so, we get. And we're finding here, if I evaluate the function at 0.5, I get a negative number. That means this is coming from below. So therefore, the rational function will tend up to my root, cross my root, then it will pull back and start to approach my quadratic asymptote. The same analysis can be done on the left-hand side. However, if you make the observation that as I approach my vertical asymptote from the left, if I was coming from below, I would have to tend up and eventually tend towards my quadratic. This would require me to have an x-intercept here, which I do not have. So the only option here must be coming from above, and then it'll turn around and start tending towards your y equals x squared asymptote. So what we have here is a graph of our rational function r at x with a quadratic asymptote. Thank you.